Okay, today we are going to talk about logarithmic functions and their graphs. And to first introduce this, I'm going to go ahead and compare logarithmic functions with exponential functions. So here's the definition for logarithmic functions. We're going to say if x is greater than 0 and b is greater than 0 and not equal to 1, then we have the following definition. Log base b of x equals y if and only if it is true that b to the y equals x. So let's just break this down a little bit. So we have our usual definition of exponential functions here. Notice that the a is missing. The a can be there, but for now we're just going to focus on just the base b. And if you compare the exponential form to the logarithmic form, what you'll see is, for example, if I was given, let's say 2 to the third equals 8, which is true, 2 cubed equals 8, this means that log base 2 of 8 equals 3. One way I like to show people how to read logarithm functions is kind of like a circular pattern here. So what you say is log base 2 of 8 equals 3. And that's exactly how I got this expression here. Log base 2 of 8 equals 3. And actually it works going the other way as well. So if you were to read the logarithmic function first, you would say 2 is your base raised to the power of 3 equals 8. So it kind of follows that nice circular form there. Okay, and the real takeaway for what this is saying is that actually, kind of informally, exponentials, meaning exponential functions, and logarithms have an inverse relationship. Okay, meaning that they kind of undo one another. And if you go back and look at the definition of inverse functions, really what that means is if f of x and g of x are inverse functions, then f of g of x, which is a composition of function, equals x. But not only that, also g of f of x also equals x. These both must be true in order for f and g to be inverse functions. So if you think of your f of x as the logarithmic function in this case, and your g of x function as exponential function in this case, then if you take this function and a composition with this function, you would get the result x, and vice versa. If you did this function with a composition of this function, you would also get x. Also remember that graphically, this means that if I were to graph this function and this function on the same coordinate plane, they would actually be the exact same graph reflected over the y equals x line. So if I graphed this graph, then I reflected over the y equals x line, I would get this graph. So I can kind of see this relationship graphically as well. Okay, so let's go ahead and review some basic properties of logarithmic functions. Okay, so some basic properties, we'll say properties of logs. Usually you'll see LOGS, log, short for logarithms, just because logarithms is kind of a long word. And I'm going to stick to my same definition of logarithms on this page, okay, where if x is greater than 0, b is greater than 0, and not equal to 1, then log base b of x equals y. If I look at things a little bit more closely, there's a few properties that I get. So we'll say first, it is true that log base b of 1 equals 0 because, again, think about the circular motion. B to the 0 equals 1. So these properties kind of fall very nicely if you kind of follow the exact definition and think about that circular relationship that we have here. That circular relationship, by the way, is not a formal way of thinking about things. It's just kind of a nice way to remember the relationship. It's kind of just a nice trick that I learned. Also, we have log base b of b equals 1 because, and if you think about this, you should be able to see the reason why. B to the 1 equals b. Okay. Then we have log base b of b to the y. So we have a logarithm with the argument here, b being raised to an exponent of y. And this is equal to y because, now this one you have to kind of pay attention here, b to the y, okay, b to the y equals b to the y, right, which is obviously true. It's the exact same statement here. So if you're confused on that, again, just write b to the y, which is what I have here, is equal to b to the y, which is over here. Okay, so you get a true statement if you follow that definition of the relationship between exponents and logarithms. And the fourth property here that I'm going to point out is very similar to the third one in the sense that kind of logarithm of base b of an argument of b, you're left with this exponent up here. But instead, I'm going to do b raised to log base b of y. Okay, or you can say x if you want to kind of keep things a little bit separate here. So we'll just write x here just to avoid confusion. And this, if you look at the definition here, b raised to logarithm base b, because these are inverse functions, I would actually be just left with x. Okay, and that is because, again, use our relationship here. B to the x, okay, equals, well, I guess the better way to think about it is the fact that I have a b raised to a logarithm base b. Like I said, since these are inverse functions, I'm actually just left with the x here. So that kind of circular motion rule doesn't follow quite as nicely with this. Okay, what you're actually doing in this case is you're taking a logarithm base b of both sides, which we'll get more to when you talk about equations. So just kind of as maybe as a side note here, if I were to take log base b of both sides here, so this is kind of a foreshadowing of when you solve equations, and then I take this whole guy and put it in here. In other words, taking the logarithm of both sides. Whoops, forgot the b. And then the argument on this side is just x. Then you can see that based on the previous property, log base b of b equals whatever is left here, this log base b and b would cancel in a sense, in the sense that they are inverses. So I'd be left with log base b of x, which was the exponent, if you will, up here. Okay, and this side is simply just log base b of x. Okay, and you see that you get a true statement, which is true because you can see that they're the exact same letters in the exact same spots, both involving logarithms. So to finish this statement up here, log b to the log base b of x equals x because of this statement here. So because log base b of x equals log base b of x. Okay, and I just want to point out here that there are two most common logarithms. Actually, these are the only logarithms that will show up on, for example, a TI-83 calculator. So let's talk about that real quick. Again, I'm using the shortened version of logarithms, which is logs, okay, which you'll see show up a lot on your calculator, for example. Okay, so the most basic one is a logarithm of base 10. Okay, now this you will not see the 10 written. So for example, if I write log base 10 of 1 equals, and you can take a second and see if you know what this logarithm would equal. And the way you would do that is, again, 10 to what power equals 1? Well, that has to be 0. Okay. But my point is that instead of having this 10 written here, right, you can actually just kind of have a shorthand version and just write log of 1 equals 0. And it's understood that this is a base of 10. So you don't even have to write the 10 there. Okay. Similarly, you could say, as another example, you could say log base 10 of 10. Notice how I didn't write the 10 that time, equals what? And then again, to do this, you'd use the definition and kind of that circular trick that I showed. 10, again, we know this is base 10 because there's nothing written, kind of like when you say square root, you don't write the 2. So 10 to what power equals 10? Well, that has to be 10 to the first. So in other words, log base 10 of 10 equals 1. Okay. The other most common logarithm base is when you are talking about the natural logarithm, which if you compare to exponents, you will see the base of e. So the base of e, so log of base e, okay, e being Euler's number, okay, and just as a side note, this is pronounced Euler, okay, not Euler. So we have log base e, and instead of saying, for example, log base e of, let's say, 1 equals something, okay, so if you want to evaluate this, e to what power equals 1, well, that would also be 0. Okay, but instead of saying log base e, what you can say is you can just say ln, okay, of 1 equals 0. Okay, so you can kind of think of the ln as, I like to kind of think of it as natural log, since that is what this is called. So let's make a note of that. So this is log base e. This is known as the natural log, okay, or natural logarithm, if you will. Okay, so let's talk about some of the features of logarithms, specifically their graphic features. So just like graphing exponentials, you can also graph logarithms. So let's do an example here. So let's say y equals log base 6 of x minus 1. So notice I don't have a more common logarithm here. I have a base of 6 instead of base of 10, or e, minus 5. Okay, so let's just talk about this for a second. The properties of these functions actually transfer very nicely as far as the shifts and translations. Those are two words that mean the same thing. The vertical stretches, the reflections of the x-axis or the y-axis, and all those good things. All those rules still apply here. So if I said my parent function, just as a side note, let's say the parent function was y equals log base 6 of x. Okay, I would say the transformations from the graph of y here, let's call it y1, 2, y2 would be a shift or a translation, however you want to say it, right 1 unit. Okay, so you have the -1 here, which if you haven't caught the pattern, the horizontal translations or shifts are always the opposite of the number that's next to the x. And then I also have a shift down 5 units because of the -5 attached to the end here. You could have a 2 out front here, which would be a vertical stretch by a factor of 2. You could have a negative number out front, or a negative sign out front, which would be a reflection over the x-axis. You could have a negative next to the x in here, which would be a reflection over the y-axis. So all those transformations, all those rules transfer very nicely over to these functions. Okay, so let's actually go ahead and graph this guy. We'll just kind of make our coordinate plane here. Okay, and what you're going to notice is I don't need a whole lot of points to get the graph of this down, but I do want to have, maybe 2 or 3 parts of the graph up there just to get a decent sketch at least. These are just sketches. So this is my origin here, 0, 0. And how I'm going to do this is I'm actually going to evaluate a few points. Okay, so let's just do this little table over here. And I kind of want to be smart about the points I pick, because logarithms, just like exponents, there's certain values that maybe make it a little bit easier to graph than others, whether the numbers are too big, too small. You can run into a whole lot of different things. But if you look here, if I plug in or evaluate this function at 2, okay, so in other words, plugging in 2 for x, okay, I would get log base 6 of 2 minus 1, which is log base 6 of 1, okay, and we know that log base 6 of 1 equals 0, because 6 to the power of 0 is 1. Okay, so this whole thing, if I evaluate it at 2, I get 0, and then 0 minus 5 is negative 5. So I have a point at 2, negative 5. Okay, and another number that would be quote-unquote smart to pick would actually be 7, because if I plug in 7 for x, 7 minus 1 is 6, and log base 6 of 6 equals 1. Again, because 6 to the power of 1 is 6. So if I evaluate this at 6, I get 1 here, and then 1 minus 5 is negative 4. So I have a point at 7, negative 4. Okay, so I can go ahead and graph that. So 2, 3, 4, 5, 6, 7, 2, 3, 4. So that's about right there. So my graph obviously is not going to be perfect because it's a very rough sketch, especially since I drew the coordinate plane myself. But you can see that it's starting to take shape here. And usually I like to just have those 2 points there. But one of the main other features that you need about logarithms is the following. There's actually a vertical asymptote at 1. The reason for that is because if I evaluate this function at 1, imagine what I'd get. 1 minus 1 is 0. Log base 6 of 0. Let's talk about that for a second. Log base 6 of 0. Okay. If you go back to our definition of logarithms, way back at the front, there is a restriction here that says x must be greater than 0. So not only can it not be 0, but it also cannot be negative numbers. So if I go back to my problem here, I actually am violating that rule by having 0 in here. Now the reason you cannot have logarithms of the number 0 is because what would you get for this? Well, let's test it. 6 to what power is 0? So that's kind of the question we're asking here, right? 6 to what power? That's a question mark. is 0. Well, if you think about this for a second, there is nothing that I can raise 6 to get the power of 0. So this is undefined, okay? So that undefined part is where I get this vertical asymptote, okay? So my graph, if I were to go ahead and finish this, it would look something like this, okay? So you can see that it's approaching this vertical line at x equals 1, but it never touches it, and then it's increasing as I go left to right here. Also, if you notice, let's say I tried to plug in something to the left of positive 1. For example, let's say I did log base 6 of, let's say I plugged in, I don't know, negative 1 here. Then I'd have log base 6 of negative 2, okay, negative 1 minus 1. And then I'd have the minus 5, right? But I'm focused on evaluating the logarithm now and seeing where the issue comes in here. So we say, what does this equal? Well, the question that you're really asking is 6 to what power equals negative 2? And if you think about this, we also have an issue here because I can't raise a positive number to some other exponent and get a negative number. That's impossible. So this would also be undefined, which is why this whole side of the graph is not included. Okay, so those are some of the basic features of this graph. I'm going to do one other one that involves the natural logarithm, just to throw in the number e, or Euler's number there. So let's do another example. And let's call this example 2. Let's say y equals ln. Okay, I'm going to use the natural logarithm notation here of x minus let's say 1 plus 4. Okay, and I'm not going to go through the transformations. You can do that yourself. You'd see there's a shift right 1, a shift up 4. Let's actually throw in a negative here too, so there's a reflection over the x-axis. And I'm going to go ahead and graph this guy. So right away, you should see that there is a vertical asymptote at 1. So we can label that. Okay, it won't always be 1. I just chose the x minus 1 to be in the argument here, like the last problem. Okay, and if I make a table of values here, x, y, okay. So remember that this is a logarithm with a base of e, okay, which is approximately equal to 2.718, and it's an irrational number. It's in the same family as pi. So just keep that in mind. So let's be smart about our points here. So one point I can plug in is 2. So I'd have 2 minus 1 is 1. Okay, so I'm looking at negative ln of 1 plus 4. Okay, where this whole thing here is saying e to what power is 1? Well, we know that that is going to be 0. 0 times the negative is still 0. 0 plus 4 is 4. Okay, so again, what I did there is, so a little side note, ln of 1 is equal to what? Well, you know that this is a base of e, so e to what power is 1? Well, that has to be 0. Okay, so I have a point at 2, 4. Okay, another point that I'm going to plug in here is actually, I'm going to be a little tricky here with the point I pick. I'm going to choose the point e plus 1. Okay, now the reason that I chose that is because if I evaluate this function at e plus 1, you'll see that the negative 1 and the 1 cancel each other out, so I'm left with ln of e. So in other words, I have negative ln of, if I were to plug in everything at once, e plus 1 minus 1 plus 4. Okay, where this is the, let me highlight it here. This is the part that I plugged in, and then I have the minus 1 that's still here. So in the end, this becomes negative ln of e plus 4. And we know that ln of e is what? Well, it's whatever e to some power to e is, so that has to be equal to 1. So this is equal to 1. So then I'd have 1 times a negative is negative 1. Negative 1 plus 4 is 3. So I have a point at e plus 1, comma 3. Now you might be wondering, well, what is e plus 1? Well, we know that e is 2.718 roughly. So just add 1 to that, you get something between 3 and 4. So somewhere between here you can just approximate it. So you have the point e plus 1, comma 3. 1, 2, 3. So somewhere right there. And what you'll notice is if you keep graphing this, it's going to decrease like this. The reason for that is because of this negative. Originally it would go like this. Now I reflect it over the x-axis, so it goes down like this. So my graph actually looks like this. Again, approaching this vertical asymptote here. Okay, so there you have the definitions all the way back at the beginning of logarithmic functions, compared them to the exponential functions and how they have an inverse relationship. Then we talked about some of the basic logarithm properties here. We talked about, most of the time you'll see log base 10 or log base e, which is the natural logarithm, e being Euler's number, especially if you're looking at a TI-83 calculator. And then we have two examples of graphs here, one with a base of 6 and one with a base of e, in other words, the natural logarithm.